Welcome back to Physics 191. I'm Gerard Blanchard. Last time, we introduced the concept of energy, and we introduced several forms of energy. So before we move on, I would like to review those forms of energy. The first form of energy that we talked about is kinetic energy, or the energy of an object's motion, or I should say the energy that an object has when it moves. We can measure or calculate kinetic energy as 1/2 of the object's mass times the object's speed squared. Or in other words, if we represent kinetic energy with K, then K would be 1/2 m times v squared. Now that is the object's speed. It doesn't matter whether the object is moving in the x direction or the y direction or both. V would be the magnitude of the velocity, or in other words, vx squared plus vy squared. Speed is a scalar, mass is a scalar, and that means that kinetic energy is also a scalar. Kinetic energy is not a vector. It doesn't have direction. So an object moving with a mass m, moving with a speed v, has kinetic energy 1/2 mv squared, regardless of the direction that it's moving in. And you'll see that that's part of the advantage of using these energy ideas, is that we don't have to work with velocity vectors. We can just work with speed. That will simplify our calculation somewhat. So, when an object of mass m moves at a speed v, it has kinetic energy of 1/2 mv squared. That's our first form of energy that we'll consider. The second form of energy that I introduced was potential energy. Specifically, we'll have two different types of potential energy. Gravitational potential energy, which is the energy that an object has from being in a gravitational field. When we're near the surface of the Earth, where g is a constant, then we can calculate the gravitational potential energy of an object as the object's mass times the gravitational field strength times the height of the object. Or we'll represent potential energy with a U, so that U sub g, or potential energy from gravity, is equal to m, the mass of the object, times g, which is 9.8 newtons per kilogram, times h, or the height of the object. Now this is important. You are free to choose where you call height equal to 0, which means that you're also free to choose where you set potential energy equal to 0. That also means that potential energy could be negative. If I were to, for example, call the height of this table to be height equals 0, then any object on this tabletop would have 0 potential energy. Any object above the tabletop would have positive potential energy, and any object that fell off of the table and was below the tabletop would have negative potential energy. So potential energy can be positive or negative, or gravitational potential energy can be positive, negative, or 0, and that's okay, because the only thing that, as you'll see, the only thing that matters is change in potential energy. The absolute value of an object's potential energy isn't important. What will matter when you see our equations is the change in potential energy. Or in other words, as I lift this pin from the tabletop to here, I've increased its height and I've increased its gravitational potential energy. As I let it go, as I move it back down to the surface, the potential energy decreases. So we have a gain in potential energy and a decrease in potential energy. So gravitational potential energy, which we'll represent with a U for potential energy, sub g for gravitational, equals mass of an object times g, 9.8 newtons per kilogram, times the height of the object, where you are free to decide what you're going to call height equals 0. The final type of energy that we'll consider is elastic potential energy. That's the potential energy that is stored in an object that is stretched or compressed. If you imagine, for example, that I have a spring, and let's say that this spring is about this long. Visualization is important in physics, so you'll have to imagine my spring. If you imagine a spring that is naturally this long, and I compress it, then I'm putting energy into the spring. Compressing the spring puts energy into it. If I were to stretch it, I would also put energy into the spring. Imagine, for example, that I put the spring on the tabletop and I compress it, then I put energy into the spring, and that energy could be used, say, to launch an object into the air once I release the spring. So I could put a ball on a spring and compress it, and when I let go, the potential energy of the spring would convert into kinetic energy of the ball, and eventually gravitational potential energy as the ball rose up in the air. So compressing an object or extending an object puts elastic potential energy into that object. As another example, imagine that I'm holding a slingshot with a rubber tubing. As I pull back on the slingshot, I'm extending the rubber tubing, and that's also putting potential energy into the slingshot, which once I release it, it will be converted into kinetic energy of whatever it is that I'm shooting with the slingshot. So elastic potential energy is the third type of energy, the second type of potential energy and the third type of energy that we're considering here. To calculate elastic potential energy, we have to know two things. We have to know three things, actually. One is, what is the natural or unstretched length of the spring? And that would be L0, the length 0, the unstressed length of the spring. L would be the stretched or compressed length of the spring. And K is something called the spring constant. The spring constant has units of newtons per meter. That's actually newtons of force that it takes to stretch the spring by 1 meter. And that is a measure of the spring itself. Now I keep saying spring because a spring is the prototypical elastic object. You can compress it, you can extend it, and it will, once you release it, it'll come back to its original shape. Another prototypical type of elastic object would be a rubber band. You can stretch a rubber band, and then when you release it, it will come back to its natural shape. Now, a rubber band, if you have a loose rubber band, compressing it doesn't put potential energy into it. So a rubber band would only have potential energy when you stretch it. So that'll be something that you'll have to realize when we do some exercises later on. We'll have somebody bungee jumping off of a bridge, and we'll have to calculate the elastic potential energy of the bungees. So, to calculate the elastic potential energy, which we write as U for potential energy, sub E for elastic, that is 1/2 of the spring constant K times the quantity length minus length 0 squared, or UE equals 1/2 K times L minus L0 squared. Now, since K is a number that's always positive, and length minus length 0 squared is always positive, elastic potential energy is always positive. The smallest it can be is 0 when the length is equal to the unstressed length. So at the unstressed length, there is 0 elastic potential energy in the spring or rubber band or bungee. And as it is either compressed or stretched, then elastic potential energy increases. Okay, so that's our Those are our three forms of energy that we know so far. Kinetic energy, 1/2 mv squared. Gravitational potential energy, mass times g times h, mass of the object, g, 9.8 newtons per kilogram, and height relative to whatever we choose to be the height, the zero height. And finally, elastic potential energy, 1/2 k times the length of the spring or bungee minus its unstressed length squared, or UE equals 1/2 k L minus L0 squared. Okay, now that we've talked about the types of energy that an object can have, we should talk about changing the energy of an object. And to change the energy of an object, you must do work on it. Now, the word work has a particular technical meaning in physics. Work is equal to the force applied to an object times the distance that it moves times the cosine of the angle between the force and the motion. So let me give you a few examples. As I take this pin here and I place it in my hand, I am exerting a force on it, but it's not moving, so at this point I'm not doing any work on it. If I were to lift it up, however, then I am applying a force to it. That is upwards. I've moved it a distance that is also upwards, so that the angle between the force and the direction of motion is 0. So the work that I've done is the force that I'm applying on the work that I did in raising it is the force that I'm applying to the pin times the distance that it moved times cosine of 0, which is 1. So as I lifted the pin up, I did a positive amount of work on it, and I've increased the pin's energy. I've increased the pin's potential energy. As the pin went from the tabletop to up here, it increased in height, so it increased in potential energy, and it did that through the action of my work. I did work on the pin to lift it up. Now how about if I lower the pin back down to the tabletop? Well, as I do that, then I'm still applying a force upward. My palm or my fingers are pushing upward on the pin, but the direction of the motion is downward. So we have an upward force on the pin times downward motion, and now those two are 180 degrees apart. So we have the amount of force that I applied to the pin times the distance that it's moved times the cosine of 180 degrees, which is minus 1. So as I lower the pin from this position to this position, I've done negative work on the pin, or in other words, I've reduced its energy. And as you can see, I reduced its potential energy. It has some positive amount of potential energy up here. As I lower it back down to the tabletop, it has less potential energy. So I've reduced the potential energy of the pin by doing work on it, by doing negative work on it. Now, if I were to move the pin sideways, either way, I'm doing 0 work on it. I'm not increasing or decreasing its energy. You can see that its potential energy is unchanged, but how is that 0 work? Well, the force that I'm applying to the pin is upwards. The force is upwards. The motion is to the right or to the left. Either way, the force and the motion are at 90 degrees. So force times distance times cosine of 90 degrees is 0. So that is what we mean by work in physics. Work is the force applied to an object times the distance that it moves while you're applying that force times the cosine of the angle between the force and the motion. And so that theta is important when you're calculating work. So, if we think about it once again, I'm applying a force to the pin. I'm moving it a distance up. We have force times distance times cosine of 0 degrees between force and motion. So that would be force times distance times 1, which is a positive amount of work. In this case, force upwards times distance moved, which is downwards, would be force times distance times cosine of 180 degrees, or force times distance times -1. So that is a negative amount of work, and I've reduced the pin's potential energy. And finally, as I move the pin sideways, either to the right or to the left, I'm not increasing or decreasing the pin's potential energy. So the work that I'm doing is 0, and we can see that by force upwards times the direction of the motion being to the right or to the left. Either way, that's force times distance times the cosine of 90 degrees, which is 0. So positive work, negative work, 0 work. Now, one thing to realize is that we are only concerned with work done by what are called non-conservative forces. A non-conservative force is a force that is not a conservative force. Now, what is a conservative force? A conservative force is a force for which we have a potential energy. So, for example, gravity. Gravity, since we have a potential energy function for gravity, gravity is considered a conservative force. Now, the force exerted by a spring or an elastic band, since we have elastic potential energy, that's also a conservative force. So, at this point, you know of 2 types of conservative forces: gravitational potential energy and elastic potential, gravitational force, which gives an object gravitational potential energy, and the elastic force, which gives an object elastic potential energy. Now, I'll give you a hint of why we consider these to be conservative forces. If I lift up this pin right here, I have given it positive gravitational potential energy. Now, if I let it go, then it will fall down under the effect of gravity. So the object's gravitational potential energy will spontaneously decrease. So if I let it go, it falls down, so that the pin started with positive gravitational potential energy. Under the effect of gravity, it fell down, but the total energy of the object was conserved, was kept constant, because the gravitational potential energy turned into kinetic energy as the object fell. So the gravitational force didn't change the total energy of the object. It only changed the gravitational potential energy. It decreased the gravitational potential energy, but it increased the kinetic energy. And when we talk about total energy of an object, we mean kinetic energy plus potential energy. So the amount of gravitational potential energy that this pin has right now is completely converted into kinetic energy as the pin falls under the influence of gravity. So forces that have a potential energy function associated with them are called conservative forces. This is something important to remember, because we'll be analyzing situations and I'll ask you to find the non-conservative forces, because we have to worry about the work done by non-conservative forces. We don't have to consider the work done by conservative forces, because we will already account for that with our potential energy. Okay? Another example of gravity conserving the total energy is if I were to throw this pin up. If I were to throw it up, and let's just imagine that for a second, if I were to throw it up, then once it left my hand, it would have some kinetic energy. It would have some speed, so it would have kinetic energy. And as the pin rose up, it would slow down, so that the kinetic energy would be changed to potential energy. So as the gravitational force slowed the pin down, the pin would lose kinetic energy, but it would gain an equal amount of gravitational potential energy. So if I throw it up, then once it left my hand, it rose up, losing kinetic energy, but gaining potential energy until it came to rest up here at the top under the influence of gravity. And then, as it came back down, it would gain kinetic energy while losing gravitational potential energy, but those two would always be in balance. So the gravitational force doesn't change the total energy of an object. Total energy being kinetic plus potential. So gravitational force, or weight, is a conservative force. The elastic force, the force exerted by an elastic band or a spring, is also a conservative force. So we don't have to calculate the work done by those forces. We've already accounted for it in the potential energy. Next semester in Physics 192, you'll encounter another potential energy, or another force with a potential energy associated with it, and that'll be the electrical force with the electrical potential energy. So the electrical force is also a conservative force. So gravitational, the weight, which has gravitational potential energy, elasticity, or the force of a spring has elastic potential energy, that's also a conservative force, and electrical is a conservative force. So that when you make a calculation based on energy, you don't have to calculate the work done by those forces. That is already accounted for by the potential energy. So, if I am going to put what I've been telling you into an equation, we need an equation if we're going to answer questions in physics. The equation would be that the change in an object's energy, which I'll symbolize with an E, an object's total energy, is equal to the work done by non-conservative forces on that object. Or in other words, delta E equals work sub NC, which means the change in the total energy of an object is the work done on it by non-conservative forces. Let's expand that equation a little bit. If I write that the total energy of an object is the object's kinetic energy plus potential energy, or E equals K plus U, then the change in an object's total energy would be equal to the change in K plus the change in U, or change in kinetic energy plus change in potential energy, or delta E equals delta K plus delta U. The change in energy, let's expand those deltas. The change in kinetic energy is the final kinetic energy that an object has at the end of our interval minus the initial kinetic energy that an object had at the beginning of whatever interval we're considering. And similarly for the change in potential energy, that would be the potential energy final at the end of the interval under consideration minus the potential energy initial, the potential energy that the object had at the beginning of the interval. Or in other words, delta E is equal to K final minus K initial plus U final minus U initial. And finally, we bring in the idea of work, or the change in energy is the work done by non-conservative forces. And we can put that all together. We have change in energy twice, and we put both of those together to derive the equation. The final kinetic energy that an object has minus its initial kinetic energy plus the final potential energy that an object has minus its initial potential energy is equal to the non-conservative work done on that object during the interval under consideration. Or in other words, change in kinetic energy plus change in potential energy equals the non-conservative work done on an object. And that leads us to our new type of situation, which is an energy situation. So we have an energy situation. How do you identify a situation that can be handled with energy considerations? And you recognize that because it's a question that's concerned with a change in speed and change in position of an object and not time. Change in speed is a change in kinetic energy. Change in position is a change in potential energy. So speed should make you think kinetic energy. Position should make you think potential energy. And so far, we haven't discussed time at all in the context of energy. So far, energy can't deal with time. It can only deal with a change in position and a change in speed. When you identify an energy situation, you have the general equation, or the starting equation, of change in kinetic energy plus change in potential energy is equal to the non-conservative work done on an object. Let's try an example. Josie and Charlotte push a 12-kilogram bag of playground sand for a sandbox on a frictionless, horizontal, wet polyvinyl surface with a constant horizontal force for a distance of 8.0 meters starting from rest. If the final speed of the sandbag is 0.4 meters per second, what is the magnitude of the force with which they pushed? Now you can recognize that you have a change in position, you have a change in speed, so this is a candidate for using energy to answer this question. You will start, as always, with a diagram. Draw a diagram, draw the initial situation, the final situation, draw in all the forces, and then you, recognizing this as an energy situation, you would start with your general equation, change in kinetic energy plus change in potential energy equals the work done by non-conservative forces on the object. So I would like you to try, set that up, get started, and try and stay ahead of me. I'll help you in a moment. Okay, our diagram, as usual, has the bag of sand. It's pushed some distance on a horizontal surface, so we'll call that horizontal surface X. And let's see, we know that the mass is 12 kilograms. What else do we know? We know that there is a constant horizontal force that pushed, so we'll call that force applied. And let's think about the other forces that are acting on the object. Well, we have weight. We have the normal force. And we know that it was pushed a distance of 8 meters, so X initial is, we'll call that 0. X final, that is 8 meters. The sandbag started from rest, so V initial equals 0, and its final speed was 0.4 meters per second. Put my units there. And what we're asked for is the magnitude of the force with which they pushed. So we have a object that changes its position, changes its speed. We can recognize that this is an energy situation. And we start our energy situation with work done by non-conservative forces is equal to the change in kinetic energy plus the change in potential energy. We'll expand this out a little bit. The work done by non-conservative forces is kinetic energy final minus kinetic energy initial plus potential energy final minus potential energy initial. Well, if we consider the ground to be height equals 0, it really doesn't matter what we consider the ground, but let's consider the ground to be height is equal to 0. That would tell us that our gravitational potential energy is 0, both initially and finally. Or, if we were to say that the ground were any height other than 0, that still wouldn't matter, because whatever mgh we had to begin with, we would have the same mgh at the end, so that u final minus u initial would be the same. So the potential energy of the bag doesn't change at all. So this term is 0. Kinetic energy initial is also 0, because the bag started with 0 speed. So we know that kinetic energy initial is also 0. Now this is common to energy situations. You can often zero out most of the terms. So we have the work done by non-conservative forces is the kinetic energy final, which is 1/2 mass times V final squared. And we know the mass and we know V final squared, so we can actually calculate the work done by non-conservative forces. Now, we have to expand work non-conservative to find the work done by the non-conservative forces. Let's think about our forces. Our first force that we'll consider is weight, or the gravitational force. That is a conservative force because we have accounted for gravitational potential energy. So that is conservative. So weight is a conservative force. We do not have to consider the work done by it. However, the normal force and the applied force do not have potential energy functions, so those are both non-conservative. So both the normal force and the applied force are non-conservative, so we have to consider the work done by both of those forces. Well, let's see. Work is force times distance times the cosine of the angle between the force and the motion. So we have the applied force times the distance moved. The distance that the box moved is 8 meters times the cosine of the angle between the applied force and the direction of motion. And the applied force and the direction of motion are both in the same direction, so the angle between those two is 0 degrees. Then we have the normal force. Normal force is applied to the box, the box moves 8 meters, so normal force times 8 meters, times the cosine of the angle between the normal force and the direction of motion, and that is 90 degrees. So cosine of 90 degrees. And cosine of 90 degrees is 0, so that this entire term is 0. Because we're multiplying the normal force times 8 times 0, so all of that is 0. Cosine of 0 is 1. So that goes to 1. So we have force times 8 is equal to 1/2 the mass times V final squared. So it'd be 1/2 times 12 kilograms times V final 0.4 squared. And so we have the applied force times 8 is 1/2 mv final squared. I'm going to divide through by 8. Divide both sides by 8 to get the applied force is equal to 1/8 of 1/2 of 12 times 0.4 squared. Or the applied force is equal to 1/8 times 1/2 times 12 times 0.4 squared. 1/8 times 1/2 times 12 times 0.4 squared is 0.12, and since it's force, we know that the units have to be newtons. So the force that Josie and Charlotte applied to the box to move it 8 meters while it increased in speed to 0.4 meters per second is 0.12 newtons. So let's just review what we've done here. We drew our diagram. We have the initial position of the box. We have the final position of the box. We listed all of our knowns and unknowns, everything that we could get from the question statement, and we drew in the forces on the box. We recognized that we had a change in position and a change in speed, which made us think energy. So we identified this as an energy situation, which immediately led us to write down our energy equation, work non-conservative, is equal to change in kinetic energy plus change in potential energy, which we expanded out. Change in kinetic energy is kinetic energy final minus kinetic energy initial. We decided that kinetic energy initial was 0 since the initial speed was 0, and we decided that U final minus U initial, or the change in potential energy, was 0 because the box didn't gain height. Whatever height it had to begin with, and therefore whatever potential energy it had to begin with, was the same at the end. So U final was the same as U initial. And then we just kept on working until we found out that the force was 0.12 newtons. Okay, very good. Here's another question. Jim rides his skateboard down a ramp that is in the shape of a quarter circle with a radius of 5 meters. At the bottom of the ramp, Jim is moving at 9 meters per second. Jim and his skateboard have a mass of 65 kilograms. How much work is done by friction as the skateboard goes down the ramp? Please address this question as you did the last one. Same procedure. Realize that we have a change in position, a change in speed, must be energy. And also another hint that this is an energy situation is that we're asked for work. And work is right there in the energy equation. So that's your hint that this is an energy situation. So go ahead and draw your diagram, get all your information from the statement, and try and stay ahead of me. Okay, let's draw the quarter circle. And we're told that this quarter circle has a radius of 5 meters. So it's 5 meters both ways. We'll put Jim up here to begin with at the top. And he slides down. And there he is at the bottom. And I'm gonna draw him in the middle as well. I'm gonna draw him in right here, and you'll see why in a moment. Let's see. We have to have his height initial and his initial speed. Height final. Speed final. Well, if we call the bottom to be height equal to 0, then that would make the top 5 meters because because the radius of this pipe is 5 meters, so he was initially 5 meters above the bottom. So it would be 5. V initial, we have to infer, is 0. He started from rest. We weren't told that he was moving in the beginning, so we have to infer that. He was stopped at the beginning. And his final speed is 9 meters per second. 5 meters, 9 meters per second. His mass is equal to 65 kilograms. And we have gotten all of the information that we can from the statement. We have a change in position and a change in speed. That should make us think energy. And then we would write down the work done by non-conservative forces is equal to change in kinetic energy plus the change in potential energy, or the work done by non-conservative forces is equal to kinetic energy final minus kinetic energy initial plus potential energy final minus potential energy initial. And we stop at this point and think which of these terms are 0. Often in energy situations, you will have 0 for many of these quantities. And when he's at the bottom, height final is 0, which would tell us that his final potential energy is equal to 0. Because remember, potential energy is mass times g times height. So his final, if his height final is 0, then his final potential energy will be 0. And if he starts from rest, then if his initial speed is 0, then his initial kinetic energy is also 0. So initial kinetic energy is equal to 0. So we have the work done by non-conservative forces is equal to kinetic energy final minus potential energy initial. Kinetic energy final would be 1/2 mv squared, mv final squared, minus mg height initial. That's the work done by non-conservative forces. So the work done by non-conservative forces is 1/2 of the mass of 65, let's call it 65, times his final speed squared, and his final speed is 9 squared, minus his mass of 65 times g of 9.80 times his initial height of 5. And we see that the work done by non-conservative forces is equal to, well, we have to calculate that, 1/2 times 65 times 9 squared minus 65 times 9.80 times 5 gives us minus 552. Well, let's see, 552, negative 552, so that means that the skateboard lost energy as it went down. Or in other words, its increase in speed didn't keep up with its decrease in potential energy. So overall, the skateboard and the skateboarder lost energy, so a negative amount of work was done on it. Now, let's think about what force did that work. I've drawn Jim here in the middle, and let's draw the forces on him. We have his weight, but that is conservative. We have the normal force from the pipe, and we have friction. Okay? Well, work, being a conservative force, we don't worry about when we talk about the work done by non-conservative forces. The normal force, since he always moves along the surface of the ramp, then the normal force will always be perpendicular to the motion. So the angle between the normal force and the motion was 90 degrees the whole time he went down. So the normal force didn't do any work either. We'd have the normal force times the distance moved times the cosine of 90 degrees. So since the normal force is always perpendicular to the motion, the normal force did 0 work. That only leaves friction. And notice that friction will always be in the direction opposite his motion. So friction times distance times cosine of 180 degrees will give us a negative number. So the negative work was done by friction. So where I've written down here the work done by non-conservative forces, I can write down that that is the work done by friction, and it's minus 552 metric units for energy, which are joules. 552 joules of energy is the work done by the friction force. Or in other words, as Jim rode his skateboard down the ramp, friction took away some of his energy. He had potential energy to begin with that was converted into kinetic energy as it went down the ramp, but not all of his potential energy was converted into kinetic energy. Some of it was taken away by friction. So if there were no friction, he would have been going even faster at the bottom of the ramp. So, think about the energy situations. Think about this question. We will have more discussion of energy next time. And until then, think energy and think physics.